Welcome back to section 21.3. In this video we'll be going over example 2, which looks at how to use conservation of energy to calculate kinetic energy and then eventually the angular velocity of a 3D rigid body. So in this case we have this link here. Well, it's actually got three pieces. It's got a collar at A bar from A to B, and then a linkage from B to C, and it's going to rotate about the x-axis. I have redrawn that over here, not to scale. So we're asked to find omega 2 given all of these. So to do this, we need to, we also need to note that it starts at rest. That's important. So to do this, we need to get our equations. So the first one is principle of work and energy. So this is the default one. This looks just the same as it did for your planar rigid bodies. So anything you have there, we'll move over here. So that's T1 plus the sum of the work from state 1 to state 2. Remember, our states are position based here. Will equal to T2. And then if we can treat some of our work that is done with forces that are conservative, so things like a mass moving from one height to a new height or an elastic member, then we can change this to conservation of energy. And this is the one that I prefer to use when possible. Just a second. Of energy. And this is going to be T1 for kinetic energy. Again, if you don't like using T's, feel free to use whatever symbols you like, just be consistent. Plus V1, this is our potential energy. This will be gravitational or elastic potential energy at state 1 or position 1. Plus all of the work from 1 to 2 that is not conservative equal to T1 plus, equal to T2. This should be state 2, so position 2 and V2. So kinetic potential, and then work to get from position 1 to position 2. And if you need to, if you have multiple bodies, you can do summations on here. If you only have one body, then there won't be anything to summate, at least for the T1s and the T2s. Alright, so we're going to use this equation here. So sum of the T1, sum of the V1, sum of the work 1 to 2, not conservative, equal to T2, work T2, not work, kinetic energy, and then potential energy. Alright, so in this problem we have no springs, but we do have a mass. I can redraw this from a side profile. So we'll have our x-axis, we'll have our z-axis, we'll have our y-axis pointing out of the page. So I have point B up here, point A over here, point C down here. It will look like the origin. We can connect all of those. Just kind of build our triangle here. We can note that we have 1.2, 0.5, and 1.3 meters for each of these. If I redraw this, so let's assume that yellow is state 1. Then let's make blue state 2. So I will have the same AC, but I will come down to a new point down here. And this would be state 2, or position 2. So it'll kind of fall below the x-axis. This would be 1.3 meters. This would be B prime or B2. So if you want to call it B2, go for it. This will be 0.5. So we can kind of see how this thing will rotate. I'll go ahead and put a blue line here as well. There you go. So we start at rest, which means that we have no initial kinetic energy. Our potential energy is only due to weight. So all of these have a weight. Their weights are going to act at their centers. So I would have the weight of this thing going down and the weight of this thing going down. Now, we could choose our datum up here. We could choose our datum down here. I'm just going to use this x bar as my datum. Sorry, this x-axis as my datum. But you could choose one of the other ones and make it a little simpler if you wanted to. So right now, so this whole thing is half a meter tall, so it means its midpoint is at 0.25. So we're going to get 0.25 as our height. The weight of BC is 2 pounds. So that's this positive potential energy. We also have bar AB. So we could figure out the angles, but we note that it also is going to end up from this line A up to B, so it's also going to be at 0.25. Its midpoint in the Y direction, or sorry, the Z direction in this case. So for AB is 4 pounds. For the non-conservative work, well, there's no friction indicated in this problem, so this is just going to zero out as well. We have no external forces as well. If we had an external force, say, pushing on the rod or a moment or something, then we'd have to do our work equation. So that's going to be equal to, so we only have a single total body here, so I'm just going to say this is T2. And then for V2, our potential energy, again, we have no spring, so it's just the gravitational potential energy. So this point doesn't move, so it's just these guys. So now they're going to be at a negative 0.25 meters. All right. So the only thing I don't know in here is T2. So it's just like working at it's the same kind of process. You go find all your parts. Hopefully you get one unknown. If you don't, go find your additional equations. So in this case, T2 should come out to be 3 joules. This T2, in order to find omega, we're going to have to expand it. So from the previous example, again, we're about a fixed point or a fixed line here, so we can pick whatever point we really want on this line. Makes some sense to possibly pick point A, but we get 1/2 Ix omega x squared plus 1/2 Iy omega y squared plus 1/2 Iz omega z squared. Now I should only have rotation about the x, so these two should go away. And we could try to do what we did last time in example 1, and we could try to turn all of this into something about this x-axis. But we don't need to do that for all the pieces, only that bar AB. So let's break our Ix up. So our Ix, again, we can do this about point A if you want, just to kind of make it easier. But really it's about anything on this axis. So it's going to be the Ix of the collar plus the Ix of the linkage, so we'll just call it CB, and then plus Ix for AB, and AB will be the one that's actually kind of weird and complicated. So for a ring, which is a collar, if you look into the back of your book, you'll see a ring about its basically axis of spin. It is mr squared, but if you look at a problem, we're not given any radius of this bar, so therefore our radius is 0, which means we don't have a mass moment of inertia for our collar. It does have a mass, but not a mass moment of inertia because we neglect its radius. For CB, we're going to assume this is a slender rod. You could also assume a thin plate, but I'm going to do a slender rod for this. And so we're going to do this about its endpoint, which means we're going to get 1/3 mass length squared for our linkage. And then for AB, what we're going to do is we're going to do a bar up in this. So this is A and B, so we're going to find the kind of this x prime axis, and then we're going to rotate it using the equation we've used before down to the x-axis. So that'll be our strategy for that one. And then its equation about x bar will just be, so Ix prime is just 0 because it's a slender rod as well. So I'm using the z prime if you look in the back of the book. So about its kind of length, the axis it's along its length, it's 0 for this thing. So I need to move it down here. So just kind of working through. So again, we have 0 for this. I have 1/3. So this is for the linkage here from B to C. Its mass, it has a mass of 2 pounds. So we have to divide by 32.2 to make it into a mass. And its length, it is 0.5 long. So we're going to square that. And then to rotate this thing, I am going to need to use the equation. So we're going to use the Ix. Just a second, look it up. Alright, so it's Ix x ux squared plus Iyy uy squared plus Izz uz squared, where uy, ux, and uz are unit vectors. And then there's the products of inertia as well. But those are going to zero out because this rod, so if you kind of drew like the cross section of the rod is symmetric. So I'm going to get nice zeroing out for all of those. Alright, so let's update our thing here. So this is essentially we can call this XX, I believe, and we can call this our YY, our XX, and then that means our ZZ is out of the page. Well, actually, ZZ, this should be ZZ if I follow what the thing has. In that case, YY would be into the page. Regardless, the one into or out of the page is going to be zeroed out because when I take cosine of 90 degrees, that's going to go away. So we'll have the YY go away. The XX one, well, there's nothing here. So this one goes away because, as we saw, our Ix prime was 0, so our XX will go away because of that. So I only have this. These are all 0 out because of symmetry. All of our products of inertia are for a rod. So I only have the Izz. And so this will be the rotation of our slender rod. So when you go to the back of your book, you're going to be looking at X prime or Y prime. I know this says ZZ, but that's because of this coordinate system and not because it doesn't match the coordinate system in the back of the book. So we're going to be using 1/3 ml squared, and then our unit vector is the cosine of basically 90 degrees plus this angle, and this angle we can find using trig. So we can just use tangent. It's going to be a half over 1.2, which is 22.62 degrees. Alright, so this would then be cosine squared of 90 degrees plus 22.62 degrees. Let me get that over here out of the way of that thing. Alright. So this number is 0.005176, keeping 4 sig figs on that. This thing becomes, so 1/3, the mass of that rod is 4 pounds. So we'll go with a 4 over 32.2. Its length is 1.3. We will square that. We will multiply that by cosine squared of the angle 112.62 degrees. So when you put all of that together, you should get a 0.1553. Alright, so I'm going to copy some of this back to the back of the page so we can finish solving this. Alright, so we used conservation of energy. We found that T2 was 3 joules. Then we wanted to figure out how that 3 joules related back to our omegas. So we had Ixx omega x, Iyy omega y, Izz omega z. We had no rotation about y or z because it's fixed about that x-axis, so those both zeroed out. We then spent some time finding Ix, which we found to be this number. At this point, it's just an algebra problem. You solve for omega x, you will get that it is 19.66, and that is radians per second. All right. So, again, just to recap, we had this thing, chose to use conservation of energy, drew state 1, drew state 2, started at rest, gravitational potential energy. So I chose my x-axis to be my datum. I had this center of gravity above. No friction, no external forces, no external moments. T2 is what I was looking for. No springs, just gravity. So this center of gravity, this center of gravity down here. Calculated all of this for our one unknown, which is T2, which is 3 joules. Expanded T2 to get with our equation that we had from last time for kinetic energy. Noted that I have no rotation about y, no rotation about z, so I just have Ix omega x. To find Ix, I looked at my collar, my linkage, and my bar. I was not given a radius, so therefore this went to 0. For the bar, I just treated it as a slender rod about its end, so 1/3 ml squared. And then the tricky part was AB. So for AB, what we did is we calculated it about its original axis, where it had no products of inertia. We found that it's 0. And then we rotated it using our Ixx ux squared, Iyy uy squared, Izz uz squared, plus the 3 products of inertia times their rotations. Again, products of inertia were zeroed out because of the original orientation here. All symmetric about that slender rod. Once I found my angles and applied my math, we got a total, which we then algebraically plugged back in to our original equation and got 19.67. Hopefully that helps. If you have any questions, feel free to reach out.